Yeah, we're going to talk about the polynomial kernel of interval vertex deletion problem, which is written by Akanksha Agrawal and published in Soda 2019. So the content is divided by 5 parts, and the most involved part is section 3 or 4. So we're aiming to talk about at least half of section 4, and optionally the rest of the section 4 if time allows. So I think its title is very tough to understand in raw. So we should talk about what is this problem means actually. So we're gonna talk about some generic notions about graph modification, graph deletion problems. So graph modification problem is an intriguing type of problem. It asks, given a class F of special graphs and given a graph instance G, so is it possible to add or delete at most k vertices or edges in order to make modified graph belong to the class F? So each of them are called vertex completion or vertex deletion, edge completion, edge deletion problems respectively. And we're going to talk about the vertex deletion problem today. And there are a variety of special intriguing questions about the vertex deletion problem, depending on the class F. When F becomes the class of a cyclic graph, the problem is named feedback vertex F. Also, if F is a class of complete graph, it becomes a maximum click problem. Or F is consists of edgeless graph. In other words, independent set, and the problem becomes minimum vertex cover. And most of them are looking very hard to solve. So despite the graph modification collective very high attention for decades, it is known that most of the graph modification problem is NP hard. In detail, class F is called hereditary if any graph G belongs to F implies any induced subgraph of G belongs to F as well. Most of the property is hereditary, like planarity or acyclicity, and many others. So for any non-trivial hereditary graph class F, the F modification problem is NP hard, regardless of F and regardless of any type of modification. And also interval graph is also an hereditary graph class. It is NP hard to solve the interval deletion problem, vertex deletion problem.
By the way, I have a question. Like, I was always wondering what is how the triviality is defined on such kind of like graph characteristic. Like, say if you say the class F is like, say it has at most 69 vertex, then it is a hereditary and it is very trivial to solve in like, it is trivial to solve, but I mean yeah, so but it is not completely trivial. It is not one-to-one. Like it is not all true or all false. So I think there should be a formal line, but I'm not sure what is that. You know?
Agree, but I did not research about the definition of triviality. Yeah. But at least well-known properties are included in included in non-trivial hereditary graph class. So we don't gonna talk about much more deeper about the triviality.
Yeah, I was just curious about how did they prove the theorem. I was just curious. Yeah, but I think we can go on.
Maybe finite? Like what you just said seem to belong to the class of finite class.
Yeah, class of finite graphs.
Ah,
We do not talk about
that makes sense. Yeah.
Infinite graphs. No.
Yeah.
No,
think that makes
I
sense.
mean the size of the set is finite. Not the
Yeah, it is finite. Yeah, I think that makes sense.
Okay. If f is finite, maybe it's very trivial. Hence, we should not give up here, and we cannot solve the IVD problem. So we're gonna talk about the FPT-ness of graph modification problem. Briefly introducing FPT, a problem with parameter k is fixed parameter tractable, shortened into FPT, if it is solvable in order of fk dot and polynomial over n, where n denotes the input size, for some computable function fk. F can be arbitrarily row, such as Ramsey number or exponential, as long as it's finished and computable. So it is a type of tactics to shove all the hardness of problem into the parameter k. In the case of graph modification problem, the parameter becomes the k, the number of edges or vertices to be modified. So for example, vertex cover problem with n vertices and m edges may run in order of 2 to k multiplied with m with a pruning technique. For every edge, U or V must be included in vertex cover, and searching through the binary search tree, running a backtracking should terminate in 2 over k time. So it goes not deeper than depth k in the search tree. So elucidating the F modification problem is FPT received attention for decades. It includes the class bipartiteness and the acyclicity and chordal graph. And finally, interval graphs are proven to be accept FPT in 2015. The main author Cao is same one who wrote the paper by review by 300 IQ about the feedback vertex set. I think he is an expert in graph modification problem. So the current best complexity in interval vertex deletion is 6 over k, 6 to the k times n plus m, published by Cao. And we gonna talk about another technique, kernelization, which is the main dish of our lecture today. So take a look at the pruning scheme for a given vertex cover instance G and K. A list of these pruning schemes can be viewed as just a naive cutting technique, but after applying all these 3 schemes exhaustively, then we can note that G has at most 2 over k squared vertices. Since there are no more than k squared edges and vertices are always smaller than 2 times the number of edges. So applying the previous FPT-like algorithm, the vertex cover problem can be solved in k squared 2 to k plus n plus m time So we can notice that the complexity about K is concentrated in one term. So we now may cope with the case with small k and arbitrarily large n. So kernelization formally means a reduction steps from a parameterized problem instance xk, where x is the input and k is the parameter, to one equivalent instance x prime to k prime, where x prime has the bounded size by some function of fk prime. Where f is polynomial with k, we say the problem admits a polynomial kernel. In the case of vertex cover, the problem admits the quadratic kernel. The reduction step need not to be the polynomial. The reduction step need not to be a polynomial algorithm of k or n and any other, but it is common for a polynomial kernel to accept a polynomial kernelization algorithm. This heuristic includes the case of this lecture. So there is a polynomial kernelization algorithm and polynomial kernel for interval vertex deletion. In fact, kernelizability and FPT is equivalent in some theoretical sense, but note that FPT does not guarantee the existence of polynomial kernel. So it is still non-trivial. Even the IVD is FPT, but it is non-trivial to have a polynomial kernel. Now it is clear to see what we're gonna do today. So we're gonna talk about the polynomial kernel in IVD problem. But we know that what is vertex deletion problem is and what is the polynomial kernel, but we didn't talk about the class interval graph. So we share another few slides to analyze the class interval graphs. So I guess most of the participants know what is the interval graph is. A graph is interval where there is a line segments in 1D space, and the vertices are the segments, and edges edges appears to intersecting segments. So it is an illustration of the interval graph. One of the most important property of interval graph, is that interval graphs are chordal. Chordal means any cycles with size greater than 3 accepts a chord, which is an edge connecting non-adjacent vertices in cycle. So this is not chordal, but adding another chord to make the graph is chordal. So we can notice that the interval graph does not admit the induced subgraph Cn for n greater than 4. Surprisingly, interval graphs are possible to characterize by just adding a few types of forbidden induced subgraph and forbidden induced subgraphs with the whole called whole, which means Cn for n greater or equal than 4. So interval graph is able to classify with a finite class of few class of obstructions, which means in forbidden induced subgraphs. So there are not so much distinct obstructions. In general, there are 5 types of obstructions. So small ones are long claw, and whipping top. And net, which is included in dagger AW, and tent belongs to double dagger AW and holes. The common points of these induced subgraphs are, common property is they are called asteroidal triple, i.e. all the terminal vertices in such obstructions, two of them are connected by a path avoiding the remaining one, avoiding the remaining neighbor of the rest. So with this, we admit this as a fact. And some terminology about this asteroidal triples are classified as terminals and centers and bases. Terminals are three vertices which exactly form the asteroidal triple, and center is at most two vertices connected to all the other vertices, and the remainings are called base vertices. In the case of AW class obstruction, note that base vertices form a cordless induced path, while removing other terminals, note that BIs forms a path. So this is the one of method to classify, characterize interval graph. Another one is more interesting. It is called path decomposition. In fact, path decomposition is attainable to any class of graph, but interval graphs are the class of graphs which admits very special path decomposition. So path decomposition is a path with a list of some vertices, and all the adjacent vertices should have some common bag. The big vertex in the decomposing path is called bag, and all the occurrences of a vertex in a path should form a subpath of decomposing path P. For example, C belongs to red and green bags, and it occurs in a proper subpath of decomposing path. So to talk rigorously, it appears like this, but we don't pay too much attention about the formal description. Just notice that beta P, notice that the corresponding back to the vertex in a P. So if beta P is distinct maximum clicks for every P in a small p in the vertex P, path capital P, then P with beta is called click path or click path decomposition. So a well-known theorem is graph G is interval graph if and only if G has a click path decomposition. Both of the property is used in the paper. but I think we're gonna use the first exhaustive one in our lecture today. So the preliminaries are done. Now we move on to the main problem solving step. To set up some terminologies, let's define an IVD instance G with K. G is trivially a graph, and K is the number of vertex to be deleted. So generally, X subset VG is called solution if G without X is an interval graph. And solution X is called a T solution if it has size at most T. It is not hard to understand. And for some family of vertices W, the vertex set S is a hitting set of W, or S hits W, if W S has a non-empty intersection with every element in W. And the family W is called T necessary if all the T solutions must hit W. And obstruction is generally noted with a math BDO. Obstruction O is covered by W if there is some subset of obstruction O included in the class W, a family W. At last, a set M is called T redundant with respect to family W if for every obstruction O is covered by W or have a very large intersection, size greater than T, with M. So there is a family W and obstruction O. It must be covered by W or have a pretty large intersection with M. So all the other words are pretty generic and not hard to think intuitively. But what do you mean by necessary and redundant? To spoil, we will eventually deal with the K+2 necessary family with family W and a 9 redundant solution M with respect to W. And there is an additional property that W is a set of subsets of M. With this additional property, we can deduce with the pretty handy argument. So to solve the IVD instance, often we carefully choose vertex V, which does not belong to M. Note that M is a definitely solution. So removing vertices in M does not help much. So we drop V and claim that X, the solution of G minus 3K, is also a solution for GK. So if it is not true, there must be an obstruction O such that VO belongs to G minus X. And this condition definitely implies that V belongs to vertex of O. Then, since O is not covered by W, O is not covered by W, we will prove that O should intersect with M with at least 10 vertices. Otherwise, O is covered by W, then there is a set Z belongs to W such that Z is a subset of vertices of O. Then X with V, being a K plus 1 solution, intersects with Z. Then X intersection of X and Z is non-empty. This is trivially contradicts to the choice of O, which should be disjoint with X. Hence, with the large necessary family and large redundant solution, we only need to consider the pretty large obstructions with highly intersecting with M. So finding a high necessary, high redundant solution pair is gives a genuine structural benefit.
I'm sorry, but can you give an insight on what is redundant and what is like necessary? Like I'm like this just looks like a code words. Like I know there is a definition, but I don't really know what is redundant or like I can't understand it.
So redundant,
like why they are doing this? Like I mean, yeah, I don't get the intuition. So yeah.
So commonly solving a graph multiplication problem, we drop some irrelevant vertex and transform it into equivalent instance.
Which is a kernel. I mean, you're trying to make a kernel, right?
Yeah, kernel.
Uh-huh.
Kernel is which is a kernel. So we carefully choose a vertex V and drop V to make a smaller instance.
Mm-hmm.
And it generally succeeds, but imagine the case it fails.
What do you mean by fail? What do you mean by fail? It isn't a valid kernel.
Yeah, it is invalid.
You didn't found the kernel.
We found the solution for very such transformed instance, but it does not work for the original instance. So
and you
in that case we should not remove V, but and we can deduce that V should belong to some obstruction O, and the obstruction O should intersect with M with very high intersection. The redundancy T means the size of intersection. First of all, guaranteeing the obstruction size at least 10 is very beneficial in interval vertex deletion, since there are very time-taking small induced subgraphs. We can exclude the long claws or whipping tops.
Okay.
Just by demonstrating it has large size.
Okay.
Can we take pause for a few minutes here? I still have to figure out what's going on.
Sorry?
Can you take a few minutes of break? I want to figure out here.
Oh, okay. We may take a few minutes of break.
Cool.
We'll resume in 35. So I think we are ready to resume.
Mm-hmm.
Okay.
So we know that if we have M and W, it is very easy to deal. Then how we find the find the real W and M in our hand? So the main lemma in this section guarantees that given an IBD instance GL, for generality, we use another parameter L. And for unfixed R, so in this case, K plus 2 goes in the place of L, and their redundancy constants 9 goes for the place of R. So the algorithm is polytime attainable to either verify that GL is no instance, or compute W and M such that W is a set of subset of M, and W is L necessary, and M is R redundant with respect to W. And moreover, M and W is polynomial size. So it's quite good news. Our desiring set is polytime attainable and has polynomial size. As a black box, we're gonna use an approximation algorithm about IVD. In the same paper of Tao, which demonstrating the 6 to k n plus m algorithm, he verified that IVD admits a polytime 6 approximation algorithm. So if the optimal is k, the algorithm finds at most 6k instance, or the algorithm finds at most 6k vertex set, which is a solution. So as a tool, we define a copy of graph G with a subset U and the integer T. So in a copy of G, we duplicate the vertices in U T times, and for example, there is a graph G, and select this vertex as U. If we apply, if we obtain the copy of UT with t equal 4, then we duplicate the vertex with a 4 replicas, and they form a clique inside the vertex, and inside each vertex. And all the replicas has same adjacency relation with the original. Why we make this? Because if G is an interval graph, it can be proven that G prime is an interval graph as well. So in this problem, we specify G prime as a copy of G with a vertex set U and the duplication number 6L plus 1. And we analyze about the return value of approx IVD G prime. Since it's a well-designed approximation algorithm, it does not die, so it returns some size of set. And if it has a cardinality bigger than 6L, we can know that the problem is no instance. So we cannot choose L vertices to remove to make G interval, a G prime interval. And there are something remaining to deal with when the approx IVD returns set smaller than 6L. So we claim that if the approx IVD returns size 6L or bigger than 6L, then the copied subset U is L necessary, singleton with U. And if A is small, every obstruction O should intersect with A, the component on G, excluding U. So by an oracle of approx IVD, we may obtain a necessary set or augment the redundancy. So we will gonna treat the detailed proof. You may read it if you want. So we can design an algorithm redundant IVD, which calculates the necessary set W and redundant solution M. So we initiate from the M0, which is the result of approx IVD, and T, which is a potential instance of necessary set. For our steps, we copy the previous MW and T, let T be empty. So for I tuple in previous T value, let it to be V, and we run an approx IVD algorithm with a copy originate with V. Then if A is bigger than 6L, we know that V is unnecessary, so we append V into WI. Else for each U vertices U with vertices A on the graph G, excluding V, which gives a redundancy about V, and we append all the U's to MIs. Then it is clear that WI is L necessary, and MI is I redundant solution with respect to WI. Since each increment of I guarantees that every obstruction which is not covered by WI intersects with MI, a newly added MI, and previous MI is M1 to M-L, also I-1 also plays the intersection with V. And the size of cardinality of MR and WR is easily bounded by recurrence relation. So here comes the intended intermission. Any questions about this procedure? All right, I'm gonna proceed. So placing 9 redundancy and k plus 2 necessity in place of R and L, we obtain a 9 redundant order of k10th solution M with respect to k plus 2 necessary family W. Additionally, we may erase all the singletons included in W and include them in the answer. Since W is k plus 2 necessary, all the k plus 2 solution hits W, which means have non-empty intersection with the singleton, and it definitely means a singleton is included in the answer. So we may assume if W belongs to math call W, then W has cardinal T at least 2. So however, to make a polynomial kernel, we still have to bound the size of G minus M. Since redundant solution is kind of approximation solution, which is a very crude approximation. If the answer size is K, we have a K10th size. However, we are designing a polynomial kernel, so remaining M and G minus M in polynomial size is is our goal. So to bound the size of G minus M, we introduce the concept of graph modules. A vertex subset C is called a module if all the vertices in C has same neighbor outside C. So if a vertex V outside the C has a pair, one of them are adjacent and one of them are not adjacent, then C is not a module. A vertex V outside C should be adjacent to all the vertex in C or none of them. Naturally, a module is a generalized concept of connected components. Since we can notice a connected component is trivially a module. By the way, we obtain the connected components in G minus M and classify them into module, in this case, module in G. So connected components are trivially module in G minus M, but it may not be module including the remaining vertex at M. So there are a few module components. And non-module components, which contributes to the whole G minus M. Then we need to bound the number of distinct components in the kernel. In this case, there are 4 module components and 3 non-module components. And the number of vertices in each component should not grow arbitrarily. So we should include this in polynomial bound. So sorting them in.
What does distinct mean here? So.
Disconnected, yeah.
No, that you told you want to bound the number of distinct components in kernel. So, like, how is it counted as distinct?
I think there is a misleading word. We obtain the connected components in G minus M, and there are a few module components and a few non-module components. If there are arbitrarily many module components with small size, it is not a kernel. So
Okay,
there
so
are,
it just means nothing. Or,
yeah, it does not
okay.
mean anything. So sorting them with the order of difficulty, bounding the number of non-module and the size of module is easy. So they are easy to deal with. And the bounding the number of module components is quite involved. And the bounding the size of non-module components is dreadful. So we don't gonna talk about the dreadful component. And the main task, the section 4 in the lecture slide, means the procedure involved. So we deal with the easy parts first. So by some kernelization scheme, it is possible to leave at most a K11 and non-module components. K11 is a bound originate from K plus 2 times M. So we suppose the contrary. If there is a vertex W in solution M, such that for at least K plus 3 non-module components, which has W as the counterexample of its modularity. So each EI has a adjacent pair UI and VI. UI is connected and UIW is adjacent, but VIW is not adjacent. So in this case, every K subset S excluding W, there is at least 3 distinct components excluding S with such U and V. And we can easily notice that this forms a long claw, which is a forbidden induced subgraph. So excluding at most K vertices does not remove this long claw. Hence, there are at most K plus 2 times M non-module components. Otherwise, we simply just include W in answer and remove W. So it was one of the easy parts. And we introduce a simple proposition to bound the size of module components. Given an obstruction O with size greater than 4 and a module component D, then obstruction is totally included in D or intersect within at most 1 vertices. In this proposition, D is general module components. It need not to belong G minus M or other mandatory subset. It is a general property for any module and any obstruction. And it is it does not belong to the original paper. So using this proposition, it can be proven that for a minimal obstruction O not covered by the necessary family W, and given a module component of D, and vertex of O and D should intersect in at most one vertex. So two-line proof is, if O is not covered by W, then O has intersection with the solution M with at least 10 vertices, and it has at least five vertices. Also, each module component definitely forms an interval graph because M is a solution. So obstruction should not be included in vertex of D. So only the latter case holds. By the way, so if there is a module component D with VD with more than k plus 1 vertices, we just erase an arbitrary vertex in V, and solve for G minus VK. Previous lemma guarantees that we can do this at least there is a module component with size greater than k plus 1. And proof is made of very simple and readable arguments. So I'm gonna skip the whole proof. So far, beforehand, any other questions? All right. So far, our bound achieved 9 redundant solution M with respect to k plus 2 necessary family W and having a size k10. And there are k11 power of non-module components, and size of each module component is at most k plus 1. Now we move on to bound the number of module components, and in this section we prove this is bounded by 102nd power of k. That's such big. Remember that the part about size of non-module component is not even discussed. So our main lemma, denoted as lemma 4.3, takes a whole slide, fits in a whole slide with a description. So given a IVD instance G with K and some arbitrary vertex set M hat is just an additional vertex set, and we in practice we deal with the M prime, M attached with M hat, which is still a 9 redundant solution. And Kel C hat is a set of module components in G minus M prime. So in polynomial time, we can do either find an equivalent instance G prime K, which is strictly induced. In other words, G prime is a strictly induced subgraph of G, or find a small set B such that for all K subset S, which has corresponding non-covered obstruction OS, with this disjoint to S, then there is an obstruction O prime such that does not intersect with S and does not intersect with VC without B. Quite complicated. At least we know that the size B is order of K 102. So we need to interpret this lemma in some kind words. To reduce the module component size, we will just use the case M hat is empty. I think another argument with M prime and non-empty M prime does not appear in whole paper. So I don't know why the author used the notion of M hat. Anyway, so we ran the algorithm about lemma 4.3 and case analysis. If lemma 4.3 gives G prime and K, then we may just solve for proper subgraph. And if lemma 4.3 gives the set B, which belongs to the vertices of module components, and we delete arbitrary V excluding B, and solve for G minus V and K. So to prove the validity, we just need to verify that K solution S for G minus V with K is also a K solution for GK. And assume the contrary, S hits W, since V does not belong to W, and minimal obstruction is not covered by W. So by lemma 4.3, there is another obstruction. And this contradicts that S with V is a K plus 1 solution, since O prime is whole disjoint with S plus V. Thus, the reduction rule guarantees that number of vertices and module components are bounded by polynomial of K. So our final goal is to construct such B to verify the lemma 4.3. Now we switch to the general case with non-empty M hat. So another handy lemma goes through. I think there is no stop from now on, so you may intervene to ask a question anytime. So the lemma states that for any distinct non-adjacent vertices U and V, and UV is not covered by W, note that it is equivalent to non-covering, since there are no singleton in the family W. Then a set of common neighbors with UV, excluding the module M prime, forms a clique. So common neighbors form almost a clique. Assume the set UV does not belong to W, and there exists a pair of vertices XY such that XY is not connected. Then an induced subgraph with UVXY forms a whole C4 whole C4. And since O is not covered by W, because X and Y does not belong to M, and UV does not belong to W. Thus, by the 9 redundancy of M, the whole should intersect with M prime in at least 10 vertices. But there are only 4 distinct vertices in O, so which leads to contradiction. So the set UV belongs to W, or these induced subgraph must form a clique. Henceforth, for each non-adjacent vertex UV without being covered by W, there is at most one module component, so-called CUV, such that CUV intersects with the common neighbor of UMV. It's a direct consequence of lemma 4.6 and denote C star to be all the collections of CUV. Then number of vertices in C star is bounded by arbitrary choice of UMV and each component size k plus 1. So the whole boundary is product of them, which is k 21st, and it is small enough. So we just care for the module components not included in C star. So we call this module components cal C prime. And by refining all the other dirty sets, we obtain that given a vertex belongs to C prime and distinct vertices adjacent to V, and they belong to M prime, then they are covered by W, or they should be adjacent. Going through a sequence of handy lemmas, we reach to a classification lemma, which is lemma 4.11. Let C in C prime be a module component, then a minimal obstruction not covered by W and intersects with C. Then, by the lemma 4.6, where is it? Sorry, there is a lag. Then each obstruction may not contain 2 more vertices of module component. So the condition that O intersects with C uniquely determines the vertex T in its intersection. And O is an AW, not a whipping top, not a long claw, not a hole. And T must be a terminal vertex. The proof goes below. So remark that the vertex TL and TR are called non-shallow terminals, and the top vertex T is called a shallow terminal. We separately deal with the case of non-shallow terminals and shallow terminal. So in the case of non-shallow terminal, we know that there is a small set, small again, A prime, such that all non-shallow terminals in VC prime excluding A prime has k plus 1 alternatives. So there is a k plus 1 subset of A prime for any non-shallow terminal outside A prime. there is a k plus 1 subset of A prime, such replaces V. So if as the k solution of G minus V is not a k solution for GK and is a shallow terminal of a non-shallow terminal of obstruction, and it leads to the contradiction with similar argument. But the construction of and the proof of this lemma is quite tedious and exhausting. So we just not look at the proof or construction. We just accept there is a set A prime with at most 41st power of size. So we take a glance at another lemma, 4.17, which is corresponding statements about shallow terminal. So there is a set A double prime, and it is small again. All shallow terminals and VC prime, excluding both A prime and A double prime, has k plus 1 alternative. Despite it is very dreadful to see all the procedure, but I think it is more valuable to look at this rather than the previous one. So let's just peek at this. We should repair some terminologies to deal with the case. So a path is called chordless. There is no, if there is a no chord. Chord was previously defined for cycles, but the path has an analogous definition. And we called P is covered by W if there is a subset of VP which belongs to family W. It is just same as the obstruction case. Then, if P is an chordless path which does not intersect with a module component C and not covered by W, then for any vertex V in V belongs to C, neighbor of V and the path can intersect in at most 2 vertices, and the intersection should be adjacent. If not, if there is a distant pair of neighbor belongs to P, then by the lemma 4.69, the double element set should be covered or should be adjacent, and each collides to a non-covering condition and the chordless condition. So the only allowed form of intersection is adjacent one. It is interesting to introduce linear algebraic tricks to obtain the A double prime set. So define M double prime as M prime with vertex of C stars and A prime. So all the vertices, all the small redundant vertices that we excluded. For all 2 subset S of M prime, denote AS as the vertices does not belong to A prime and C star, such that S is fully included by a neighbor of V. Intuitively, it means the candidate of vertices can be a shallow terminal of AW possessing S as a center. So if S is a size 2 subset, it plays a role of double dagger AW, or S is a singleton, then is a dagger AW. So denote the incidence relation vector, define an incidence relation vector for all vertices in C prime without A prime, such that if Vi belongs to neighbor of U, then its ith entry becomes 1. It's a binary vector. For an edge, if U is adjacent to both of its endpoints, then add 1 to P plus ith entry. And we, for a technical reason, we leave the last entry as 1. Note that from the observation 4.6, incidence I completely describes the possible incidence relation of U. Then we collect all the incidence U for U in AS, given a 2 subset S of M prime. Note that VS is a multiset, so there are K times of incidence U. There are K elements, not K duplicate elements in the multiset VS. And we build the basis for this vector space. So VS, we extract the first basis BS1 and VS minus BS1, which is a multiset, so it still accepts the basis, obtain BS2 and BS minus BS1 minus BS2 to obtain BS3. Repeat this K plus 1 time. And the final product is called US K plus 1, which is all the union of BSIs. So for each occurrence of V in US K plus 1, we may choose arbitrary vertex UV such that incidence vector of U equals V. So we call this U subscript V. The existence of U subscript V is trivially guaranteed. And denote the vertex set AS double prime is as a collection of UVs. Note that AS double prime is no longer multiset, since it does not have any duplicate elements. Then merge all AS double prime into a single set A double prime. We do not catch what A double prime exactly means, but at least we may estimate the size. So since the basis, cardinality of basis is bounded by representing dimension, so AS prime, a double prime has a size less than K plus 1 times P plus Q and K plus 1 P squared. Note that P is the size of M double prime. Thus, A double prime has the size smaller than K plus 1 times m prime squared and m double prime squared. So it is smaller than order 102nd to k, since m double prime is bounded with I guess 4th power of m. So to make the final argument, define a nullifying path, a nullifying vector. It's not a hard concept, but it's a mask for some certain graph. So given a vertex set x and h set y, nxy denotes the mask representing the vertex set s, x, and h set y. So include the vertices included in x is 1, and x has a value 1, and the vertex does not belong to x, has an entry 0, and so on. For a path, NP simply denotes the masking covector n by its vertices and its edges. So let P be an induced path. Induced path is a synonym of chordless path. Let P be an chordless path such that P is not covered by W. Then for all U and VC, a dot product of NP and incidence U is 1 if and only if neighbor of U does not intersect with P. Note that in an AW case, the base vertices form a path and the terminal vertex does not intersect with the basic path. Thus, the condition NP dot incidence U equals 1 directly implies that U may play the role of terminal vertex for dagger AW or double dagger AW. The proof of this lemma is not that hard, since the only possible case of intersection size is confined in 0, 1, 2. So examining each case gives a proof. This case, NP dot incidence U is definitely 0s and 1 at last case, and 1, 2 there are just even non-trivial, even non-zero entries. So we restate the lemma 4.17 that about the alternatives of shallow terminal based on the linear algebra knowledge. Let W be a vertex in C prime, excluding both A prime and A double prime, and O be an AW with a shallow terminal W. Let S be the center of O. Then for all I from 1 to k plus 1, there is a vertex in BSI. Sorry. It should be written in bold script because V denotes a vector, such that O minus W plus UV is still an obstruction. Since W is in AS, but W does not belong to A double prime, it has never been selected for the basis. So for all I in the range from range k plus 1, the incidence relation vector belongs to the vector space spanned by the BSI. So incidence W is represented by the sum of some basis vectors, and taking a dot product with the cordless path P of O, which is a basic path. The center is the S, and W is the terminal, and the basic path is P. So taking a dot product with NP, it remains that 1 equals to NP dot inc BC1 BI1 dot plus dot plus NP dot inc BIT, which indicates there must exist some J such that the dot product of NP with incidence Bij equals 1. Then O minus W plus Bij is still an obstruction, and we may choose J for all I in the range of k plus 1. So there are at least k plus 1 alternatives of a shallow terminal. Hence, all the vertices in C hat excluding a small module component sets with C star and the non-shallow case A prime, the shallow terminal case A double prime, is a terminal of some AW, and there are k plus 1 replica obstruction. Hence, with a K solution, we cannot exhaust all these replicas. So removing all the vertices except them gives an equivalent instance. So our main lemma 4.3 is verified. So our technical works are done. We move on epilogue and talk about some outlines. So any of you have any questions? All right. So we verified that the number of module components has a polynomial upper bound. Then we may solve the so-called subtask of this in this case by adding additional parameter, the vertex cover size. By adding a vertex cover X to the redundant solution M is still a non-redundant solution, and G minus M prime is an independent graph. So all the components of them are modules. And thanks to this assumption, size of each non-module components are not to be considered. However, we know the limitation of this argument, since the M prime grows arbitrarily. So anyway, to solve the whole problem, we should bound the non-module component size, and this covers the remaining section of the paper. And it is easy to guess it's a very tough job, since each section consumes about 20 pages in A4. So to reveal the exact bound, we bound the two separated components of non-module components. We adopt a click path decomposition. Then it has two non-trivial ingredients, length and each back size. So back size is bounded by 11^3 power of k, and the click path length upper bound equals a big O k 1629. Pretty annoying. So several marking strategies. Marking strategies means similar job in our main task section to introduce a small importance set and remove all the irrelevant vertices. And there are several marking strategies. And there are several case analysis. Most of the section 5 is case analysis, and most of the section 6 is introducing 7 different marking schemes with a tremendous knowledge-oriented tricks and including some other weird optimizations. I saw the Metroid-related arguments in the preliminary of the paper, and the lecture did not include a single word about Metroids. Especially, it takes a theorem about representable Metroid, which is a very specific and eerie classes. I think the tricks about this is highly related to resolve the issue in section 6. If you are interested, I'll read once. So here ends our presentation. Interval vertex deletion finally admits a polynomial kernel with a tremendous large polynomial kernel. The author believes there is about k10th kernel, and she leaves it to an open problem. On the other hand, for a simpler version, which is called corridor vertex deletion, does not talk about any AW cases, which has k13th kernel found by the same author. It uses the same tricks, and I think the author is very patient to think about such case analysis and the marking schemes to bound achieve the polynomial kernel. However, the accessible version of paper is quite faulty. There are some calculation errors and typos. As an example, she asserts that there is a 6 approximation algorithm for interval vertex deletion, but according to the reference, I think there is just a 8 approximation algorithm. It is not sure because I did not had a complementary reading of the original reference. But excluding this, there is so many typos and so many bound errors. So it was tough to review the paper, and you guys had tough time to hear on the poor lecture. Thank you for listening.